So, today I would like to explain about operational amplifiers. What is operational amplifiers? It is a linear devices that have all the properties required for nearly ideal DC amplification and therefore used extensively in signal conditioning, filtering, or to perform mathematical operations such as add, subtract, integration, and differentiation. An operational amplifiers, or OPAMP for short, is fundamentally a voltage amplifying device designed to be used with external feedback components such as resistors and capacitors between its output and input terminals. These feedback components determine the resulting function or operation of the amplifiers, and by virtue of the different feedback configuration, whether resistive, capacitive, or both, the amplifiers can perform a variety of different operations, giving rise to its name of operational amplifier. An operational amplifier is basically a three-terminal device which consists of two high impedance input. One of the input is called the inverting input, marked with a negative or minus sign. The other input is called the non-inverting input, marked with a positive or plus sign. A third terminal represents the operational amplifier's output part, which can both sink and source either a voltage or a current. In a linear operational amplifier, the output signal is the amplification factors known as the amplifier's gain A, or multiplied by the value of the input signal, and depending on the nature of this input and output signal. So, what is an ideal operational amplifiers? The ideal operational amplifiers is an amplifier with infinite input impedance, infinite open loop gains, zero output impedance, infinite bandwidth, and zero noise. It has positive and negative inputs, which allow circuits that use feedbacks to achieve a wide range of functions. Using operational amplifiers, it's easy to make amplifiers, comparator, log amplifiers, filters, oscillators, data converters, level translators, references, and more. Mathematical functions like addition, subtraction, multiplication, and integration can be easily accomplished. Practically, real-world operational amplifiers have finite characteristics, but in most applications are close enough to the ideal to make a huge range of inexpensive, high-performance analog application possible. Here are the building blocks for analog design. One key to the operational amplifier's design is nodal analysis. Since the input impedance is infinite, the current in and out of the plus signs and the negative sign input nodes defines the circuit's behaviors.
Hello everyone, my name is Shahedatul Azera Binti Saad and my metric number is 207159. Next, I will continue with the type of ops amps. Ops amps can be classified into three main types based on the input-output voltage range, which is dual supply, single supply, and rail-to-rail. The input or output voltage range of each type of ops amp is shown below. First, dual supply ops amp. Since op amps generally amplify a small signal close to zero voltage when zero voltage input is required, in the case of dual supply, op amp must be set to negative 0.5 volt or less. For this reason, a negative power supply is often used, and since both positive and negative supply are required, is called a dual supply op amp, which is low noise power supply and low offset dual supply. Next, I will continue with the second type, which is single supply ops amp, which is ground sense. When inputting a signal near zero voltage, a negative voltage is needed if using a dual supply ops amp general purpose, but An ops amp that enable input without this negative voltage is called a single supply ops amp. It's also referred to as a ground sense or op amp since it can operate up to the ground level input signal, which is general purpose ground sense, high speed ground sense, low current ground sense, low noise ground sense, and high performance ground sense. For the last type is rail-to-rail ops amp, which input or output full swing. With the recent trend toward energy conservation, a greater number of sets are being driven at low voltage. Ops amp also need to operate at low voltage, but if the VCC drops to nearly 5 volt, a single supply ops amp is able to only input 1.5 volt less than VCC, which can be inconvenient. In contrast, a rail-to-rail ops amp can operate normally even when the input voltage swings from VEE to VCC, because it can output input over the full supply voltage range. It's often called an input or output full swing to op amp, which is high speed input or output full swing, low current consumption input or output full swing, low noise output full swing, and low offset input or output full swing. Next, I will proceed with the application of ops amps. An op amp is an IC that amplifies the difference in voltage between two inputs. Ops amps can be used for various applications depending on the external component added. In the most basic circuit, ops amps are used as voltage amplifier, which can be broadly divided into non-inverting and inverting amplifier. Voltage follower, also simply called buffer, are a type of commonly used non-inverting amplifier. Ops amps are also used as differential amplifier integrated circuit. Ops amps are widely used for various applications. It's not exaggeration to say that ops amps are found in almost all electrical appliances. For example, ops amps amplify analog signal from various sensors in IoT connected home appliances and measuring instruments.
Hi, my name is Munirah Binti Razad and my matrix number is 209026. There are a few ways in which operational amplifiers are used. It used as a voltage follower, selective inversion circuit, a current to voltage converter, active rectifier, integrator, a whole wide variety of filters, and the last one is voltage comparator. Next, how operational amplifiers are wired in order to perform the operations which give its name. In this section, I just want to focus on how to wire an inverting amplifier circuit. All basic operational amplifiers have the same general functions, although they may be laid out in differing ways. For this document, operational amplifier will be used. Take a look at figure 2 on the right. The schematic for this operational amplifier. Frequently, this picture will be referred to. Notes 4.8 will be used for this project, although notes 1.4 and 8 are identical to notes 4.8. Here is the materials that you need. Step 1. Attach power supply positive, negative, and ground terminals to breadboard. Find 3 terminals inputs, which is tiny colored cylinders installed across the top of the breadboard. Take 3 banana plugs and connect them to the power supply, one in positive V port, negative ground port. You can see in the figure. Next, connect the other ends of the banana plugs into to the terminals inputs on your breadboard. It is entirely your choice which input you are using for each plug, but remember to take note which one is which. Step 2. Connect terminals to breadboard nodes. Cut and strip 3 pieces of wire, approximately the length of your index finger. Take one of the wires and connect one end to one of the terminals you just hooked to the power supply. Do the same thing for the remaining 2 wires and terminals. Next, locate the narrow vertical strips on your breadboard. They are usually denoted with positive and negative signs. Each of those represents a node that carries the input voltage along the entirety of that vertical strip. Plug each of the 3 wires into its own vertical node. You now how successfully powered your breadboard. Refer to figure to double check your work. Step 3. Install operational amplifier. Find your operational amplifier and examine it to locate the semicircular notch that is cut into the face of it. The notch denotes the top of the operational amplifier, giving you an orientation point. straddle the center of the operational amplifier across one of the vertical breaks in your breadboard, which with the notch pointing up away from you. See figure 6b. Gently press down to ensure that all legs are fully inserted. Step 4. Attach power to operational amplifier. Cut and strip 3 pieces of wire, once again approximately the size of your index finger, roughly in 3 inch. Insert one wire into the one vertical node that currently is wired to the power supply. Repeat procedure for the remaining 2 wires and nodes and find your positive charging node. If you cannot remember which is positive, physically follow the wire back to the power supply. Step 5. Wire input signal from function generator. Locate a banana to alligator clip and strip 2 pieces of different length wire. Insert one end of the 3 to 4 inch wire into the port node denoted in figure 8. Insert the other end of the same wire into a free node, a node with nothing else connected to it. We will call this node A above the operational amplifier. Find another free node. We will call this node B. Insert the 1 until 2 inch wire into the second free node. Take the alligator end of the alligator banana clip and attach it to other end of the 1 to 2 inch wire. Step 6. Take one resistor and insert one end into node A and the second lead of the resistor into node B. Take your second resistor and attach one lead to port 7's node. Attach the other lead of the same resistor to port 6 node. Examine figure 9 to ensure you correctly configure your resistor. Step 7. You can wire your oscilloscope to circuit. Strip a 1 until 2 inch piece of wire and locate another alligator to a banana wire. Insert one lead of wire into port 7. Clip the alligator end onto the other end of the wire and plug the banana end into the input port of the oscilloscope. Step 8. Powering on the circuit and setting up a testing experiment. Turn on the power supply and turn the input voltage to 15. Turn on the function of generator and set the amplitude of 4 volts. See figure 10 is an arbitrary value used for the experiment. Turn on the oscilloscope to read a value for the output of the circuit. In the experiment conducted for example purpose in this document, the output should read -8 volt and see in figure.